In this video, we'll be looking at graphing rational functions. This is slightly different than sketching rational functions because there's a lot more points and pieces of information that we would need to identify. The steps that we're going to have to identify in terms of graphing these starts off with your x-intercepts and your y-intercepts. Like most cases of functions, we should identify those values clearly. We then will want to identify your vertical asymptotes and holes, where there are any. I put those together because those correlate with your discontinuity values. You will then have to identify your horizontal asymptotes, if there are any, and your slant asymptotes. Again, you'll either have one or the other. You'll never have both. In some cases, you might not actually have horizontal asymptotes, but in most cases, you will. You'll have to plot a table of values, specifically values in between each y-intercept, x-intercept, vertical asymptote, hole, and slant asymptote if necessary. And then your last step will be to actually graph the function. So this is what we're looking to do. One thing you can help identify is if you do the symmetry of the function in the beginning, it will help you be able to register how the function should appear, specifically around your asymptotes. If those specific asymptotes need to have the same kind of symmetry on either side of it, or if it would be reflected symmetry. So let's look at this function here first, and we're going to go ahead and go through the major steps of all the details. I'm going to start with the x-intercepts because they're relatively straightforward. Don't forget that anytime you're finding your x-intercepts, you're going to set the top equal to 0 and solve. Now, the problem with that, however, is that we should probably find our domain, specifically because if the value for the x-intercept is a domain issue, again where the denominator equals 0, then that particular value is going to be a hole and things are going to get real wonky real fast. So I'm going to go ahead and find my domain. My domain is x cannot be equal to a value of 2. So when I go to find my x-intercept, remember for all x and y-intercepts you should identify specifically the entire coordinate point. So we're going to set this function equal to 0. 3x minus 3 divided by x minus 2 equals to 0. The main way that you can deal with this is if we multiply by x minus 2 on top, on both sides of the equation, the x minus 2 is going to cancel out anyway, so it's not going to correlate in terms of finding our x-intercepts anyways. So we're always just going to set the top equal to 0 and solve. In this case, if I add 3 and divide by 3, I'm going to get x equals 1. So I have 1 comma 0 as my x-intercept. If I'm looking for my y-intercepts, we're again just going to plug in 0 for x. In doing so, this is going to be negative 3 divided by negative 2. So I'm going to have 0 for my x value and positive 3 halves, because again it's a negative 3 divided by a negative 2. So I have my x-intercept and I have my y-intercept. Now we're going to go utilize this domain, identify my discontinuities, and run through the gamut of information that we have to identify. The discontinuities, again, can correlate to either being a hole or a vertical asymptote. So the discontinuity is x equals to 2, and if you recall, the way that I find my find out which the discontinuity ends up being, either a hole or vertical asymptote, is by looking at the original function and determining, can the factor of x minus 2 in the denominator cancel out with a factor on top? Now if I factor this appropriately, I have 3 times x minus 1 on top, and I have x minus 2 on the bottom. Notice x minus 2 cannot cancel out with x minus 1, and therefore if I can't cancel it out, the factor in the denominator that created that domain issue that happens to be that discontinuity is a vertical asymptote. Again, if it doesn't cancel out, it's a vertical asymptote. If it does, it's a hole. In this case, I'm going to put NA next to hole because there aren't any holes for me to have to worry about. Next, I'm going to go ahead and find my horizontal asymptotes, and if there are any, slant asymptotes. In this case, again, I'll notice that the power on top of x with x and the power on the bottom with x are both 1. And since the powers are the same, I'm going to use y equals, it's a horizontal asymptote, and there isn't any slant. Again, the way that we'd have a slant asymptote is if the power on the top was larger. If the power on the top was larger, then we would have a slant asymptote. If the power on top was smaller, then our horizontal asymptote would be y equals 0. In this case, we're going to take the coefficients of x on top and on bottom, that's 3 over 1, and therefore my horizontal asymptote is y equals 3. Now that we've identified x-intercepts, y-intercepts, my vertical asymptotes, my horizontal asymptotes, holes and slant asymptotes, if they exist, I'm going to have to plot what I have and set up a table of values for the remaining information. So over here, I'm going to go ahead and draw out this graph as clearly as possible. I'm going to start with the first point, 1 comma 0, so that's going to be right there. That's my x-intercept point. I'm going to go ahead and plot 0 comma 3 halves, so I'm going to go 1, 2, and right there is my 3 halves point. That's my y-intercept. I have a discontinuity at x equals 2. It happens to be a vertical asymptote. So I'm going to go ahead and put x equals 2 here. And I'm going to draw a dotted line up and down. And again, for every single time that you graph these functions, the vertical asymptotes, slant, and horizontal asymptotes must all be clearly drawn on the graph. If those dotted lines aren't there, then I have to assume that that graph doesn't actually taper off, that it just continues on forever in the close to approximate way that you've drawn it. So I've got my vertical asymptote. Now let me draw my horizontal asymptote of y equals 3. So I've got 1, 2, and 3. So right there is my next dotted line. Now, with all that drawn and all the information labeled, what I'm going to do is I'm going to set up a table of values very much like that of the way I did previous graphs. I'm going to go ahead and do it sideways like this. I have x and y. The x values I know and I have. The first one here is the x value of 0 gives me a y value of 3/2. I'm going to leave a space there. And I'm going to go ahead and plug in 1. If I plug in 1 for x, I get 0 for my y. I'm going to leave a space there. I know that at the x value of 2, I have an undefined value, specifically an asymptote. If you'd like, you can go ahead and draw VA here for the vertical asymptote, because there isn't actually any function value there. And now I should be able to plug in values around all of these details. The important part is that you're going to want to plug in values as far down this negative side as possible and as far up this positive side as possible, specifically so that you can help identify on which side of this asymptote will the function exist. Now, in most basic examples, such as this one, I can plug in these values and know exactly what's going to happen. I can also look at these functions and know a general idea of how the function is going to behave. After you've done enough of them, it should be relatively straightforward that the function is going to pass through a couple of these points, and it's going to taper off down towards the asymptotes like this. So again, you should be plugging in these values here. Let me go ahead and just plug in, say, -1 for this case. If I plug in -1 here to this function, back up here, if I plug in -1, I'm going to have 3 times a -2, which is going to be a -6, over a -3, and therefore that's going to give me back a value of +2. Again, it's going to be a -6 on top divided by a -3 on the bottom. It's going to give me a +2 there, and therefore that point should be, give or take, right about there. And that's graphed relatively accurately. And again, notice how it builds the guiding of that graph. I should probably plug in, say, 1/2 for in between 0 and 1. I should probably plug in 3/2 for the value between 1 and 2. I should probably plug in something like 4. Definitely something on the other side of the vertical asymptote. You'll notice that in this case, there's nothing in this space over here. We don't know what's going to happen on this side of the graph. So what we should probably do is plug in more than just 4, but maybe 5 as well. When we plug in 4 and 5, now it's important again to remember that this is not the rational function. This is just a part of it. We have to account for all possible x values you can plug in. So if you stop at the vertical asymptote and don't plug in any values over here, then this graph will not be graphed entirely, and you're going to get this particular question wrong. So if I come back up here and I start plugging in those values, say I plug in 4, that's 4 minus 1 is 3, 3 times 3 is 9, down here I'm going to have a 2, so it's 9/2 for the value there, and 9/2, you should notice, is definitely going to be larger than 3. Given that it's larger than 3, I know it's going to sit somewhere up here, and I know that the way that these functions generally behave is that they look very much like symmetrical across the vertical and horizontal asymptote. So this is probably graphed a little bit more stringent than it should. It should probably look more like this, very much like I've drawn on this other side. But the idea is still there, and that should be your rational function. Again, depending on how you graph these rational functions will build the way that they're situated. That's going to be your first example for how to graph a rational function, making sure that you remember how to identify all of these details, build your table of values, and then actually graph the function, making sure that you have those points clearly drawn in there to identify what the graph is supposed to look like.